I would like to talk about a few studies that we've done, some of them in typical infants to understand typical neurodevelopment, and some of them also in premature infants in order to understand and to explore possible disturbances related to prematurity. So I have the chance to talk just after Serena, so I can go fast on some aspects. Thank you, Serena. And actually, so you all know that when the behavioral acquisitions of the infants and the children are mainly related on the intense development of their brain, which in itself relies on several molecular and cellular processes that are overlapping and interacting during development. So first, as Serena says, we can use anatomical MRI, so mostly T2-weighted images in baby, to measure the brain growth and the brain folding. So one important aspect is that the contrast of the MRI images is changing during the first year of life. So we need to use dedicated post-processing tools to analyze these images. As Serena says, we can use these images to do some volumetry, but also some morphometry with strong changes in the folding indices that she reported. And as you can see, this process is not a linear one, but during early infancy, we can observe a kind of plateau of this folding index. Then we can go one step further and study the sulcal patterns with, for example, sulcal objects, as has been developed here by the team of Jean-François Mangin, and you will hear about this thing in the next session, so I won't talk about it. We can also use diffusion MRI to look at the development of the white matter and gray matter. So here you have some examples of images that have been obtained with the diffusion tensor imaging model with the mean diffusivity, the functional anisotropy, and we also use other parameters, the axial and radial diffusivity, to look at the maturation. So here, for example, you have examples of mapping of the connections obtained in typical babies, and here at NeuroSpin, and we can look at some markers of the maturation of this white matter tract, and in particular at the myelination by looking at changes in these DTI parameters, such as radial diffusivity. And as Serena says, we can also look at changes in the microstructure of the gray matter. So here it's the plot that she showed with this nice study from Batal and her group, using another model, the NODI model, to look at these changes in the microstructure. But even with DTI, you can look at some parameters such as axial diffusivity and see some drastic changes in the cortex with age in typical infants. And finally, on these infants, we have been able to use multimodal MRI, which means combining different markers to try to get more insights on the maturation, on the white matter bundles, but also on the cortical microstructure. And actually, this is some work performed by Jessica Lebenberg, who is also here today. And there are also some markers which directly target the quantity of myelin. And as you can see, this increased a lot in the infant brain, specifically in some regions before the others, with this codogostral progression of maturation that was described initially more than a century ago by Flechsig, for example. So all these studies in typical infants show that there is an asynchronous maturation of the brain regions, and these are actually structural, microstructural markers, but which actually translate to functional development in the brain. And for that, I would just like to mention two kinds of studies that we've done in the last years with Ghislaine Dehaene-Lambert in the babies, with studies that used both MRI and EEG in the same infants, and that related actually the speed of the functional responses, for example, here to visual stimuli, to the maturation of the white matter bundles. And also we studied with Ghislaine the progressive maturation of the linguistic pathways and suspected that these differential maturations are actually linked to the progressive acquisition of language by baby. So the main interest of neuroimaging and MRI EEG is that we can go to quantitative parameters to try to describe the inter-individual variability of the kids in their development, and this can be included in the child follow-up. So in the next slide, I would like to give you some other examples of some more recent work that we've done to try to understand how prematurity might impact this development, very early development. And I will start with studies that use the Developing Human Connectome project that Serena mentioned before, with first the work performed by Sarah Neumann and Andrea Gondova in collaboration with Thomas Ricci from King's College. And in this work, we were actually interested in connections between sensory motor regions, and we wondered whether prematurity might have a differential effect on this connection. So we studied a cohort of preterm infants without major brain lesions. So they were scored mainly as normal, and we compared them with full-term neonates, and these acquisitions were performed at 3T. And the preterms were actually scanned at term equivalent age. In this study, actually, we computed what we call the maturational distance related to prematurity, which means that we compared each preterm infant to the group of full-term neonates that were considered as a reference. So the closer to zero the distance is, the closer the preterm is to the reference groups of neonates. And here you have actually two different groups of preterms. One were born very extremely or very preterm, and others were more moderate or less preterm. And you can see that for none of these connections is a distance equal to zero. So prematurity has an impact on all the connections. Advanced, more intense prematurity has more impact on the connections, with the deep range higher, showing higher distance values than the lighter range. And in a further way, we ordered the connections according to these distances here, and we showed that there are actually vulnerability patterns of these connections related to prematurity. And these vulnerability patterns actually seem to match with the cauda-rostral progression of maturation, even if we were not able to directly test this hypothesis. So this suggests that even without brain lesions, major brain lesions, prematurity has some impact on this early development of this system. And in the following study, we wondered whether we can use these early measures to perform some kinds of prediction in these infants from the DHCP. So Andrea first considered whether she could use the cortical microstructure that Serena talked about a lot to simply predict the prematurity status of the infants. So she considered the same group as previously, with preterm infants with brain lesions, scanned at term equivalent age, and also full terms. And she actually shown with complex machine learning approaches that it's possible to predict the prematurity status based on these different DTI parameters, and by reducing the complexity of all these cortical measures into only 5 clusters of regions, with some of these clusters actually showing changes in microstructure related to gestational age at birth. So it's very small at the front. Then we tried with Andrea to see whether we can go one step further and use these early measures of microstructure to predict the outcome of the baby. So again, it's a DHCP cohort, and she used the scan very close to birth with a quite large cohort of almost 300 babies. And she used only the measure of anisotropy in the cortex to try to predict this outcome of the baby score that Serena described already. And actually, we tried to replicate a study that was published in Life by another group, the group of Wang, and we were a bit disappointed because what Andrea showed is that once you correct for the age at scan, you can predict the prematurity status in the preterm infants, but only in the big cohort. If you consider cohort of less infants, you're not different from the random level. But when it was when she went to try to predict the behavioral scores, which was what we aimed for at the beginning, actually she couldn't achieve the good prediction results. So this suggests that there is some information in these early measures of cortical microstructure, but this information is probably not sufficient to really predict the outcome of the babies. I haven't looked at the timing, so I might be late. So, in the two next slides before concluding, I would like to mention some work that we've done more recently with the group of the Robert Debré Hospital in Paris, in particular with the team of Marianne Alizon, in which we have scanned preterm infants in the context of the clinical care. And these preterm infants are again scanned at term equivalent age with different sequences. And Nicolas Elbaz actually scored all the images of the babies with a score which is quite classical for preterms, which is called the Kidokoro score. So here you see the variability of the scoring among the preterms. And in parallel to this, we applied some tools proposed by other groups to reconstruct in a nice way the T2 weighted images with super resolution, and also to segment the different tissues. So we use a tool from the DHCP, but also another tool, IBIT, from another team. And our aim with this was actually to see how clinical factors can impact this early development in preterms. So we considered whether these different factors impact the gray matter, the white matter, cerebellum, in terms of Kidokoro score and volumes. And what we observed is that, okay, all these factors might have some impact either on the gray matter or on the white matter. And on the cerebellum, it seems that, for example, only the digestive complications might be important, at least in this group of preterms. So more recently, we have acquired more data, so we need to confirm this result. In parallel to this, actually, for some of the babies, we have a follow-up with MRI at 2 months later. So we also need to analyze this data to see how these early measures evolve with maturation. And actually, in most of these babies, we also have some EEG. So this is not done in the context of clinical care. So we add this for research, recording of 5 to 10 minutes during rest. And Parvane Adipou, during her postdoc, she actually proposed to use complex analysis based on microstates. She separated the vigilance states of the babies. And for example, here she compared results in preterms and full terms during active sleeps. And actually, she showed that the dynamics of the brain can be decomposed according to different states. So we call them microstate templates. And what we see globally is that the temporal dynamics of the preterms at term equivalent ages are actually slower than in full term, and that prematurity differentially affects the network dynamics again. So as for the MRI, we also have the follow-up at 2 months. So we try to see how maturation impacts this. So in this short presentation, I aim to show you the multiplicity of markers that we can have to characterize the brain structure and the functional maturation very early on. This is particularly relevant to understand typical but also atypical development, notably in the context of the prematurity. And I couldn't resist to show you this very nice thing of why do we want markers of early development and the outcome. It's to actually set up some dedicated interventions that can try to improve the outcome of the babies. And one of these interventions that are proposed in preterm is actually this one proposed by the team of Marianne Barburot in the INCC in Paris, which is called the crawl skate. So the baby is put on a mini skateboard like this one, And as you can see, he tries to have this locomotion displacement. And they have shown that this kind of intervention can improve the outcome of preterm babies without brain lesions. And so now we are trying to see how can preterms with lesions benefit from this early intervention. And to understand this, MRI and EEG are important tools to understand the plasticity. So I thank you for your attention, and I thank all the colleagues from NeuroSpin and from all the hospitals who have been working with me for years. And probably we will go directly to the presentation from Lucy.